Hello and welcome to our next section 11.4 area of regular polygons. We're going to have to review some definitions in this particular section, but it shouldn't be too bad. Let's just jump straight into it. Regular polygons. If you remember, a couple things we need to remember. A regular polygon, well, regular means, or a regular polygon, I should say, is defined where all sides and angles are congruent. Whether it's interior or exterior angle, all of the angles individually are congruent to each other. And if you have a polygon, a regular polygon, you could actually solve for the sum of the interior angles. And we had a formula for that. For instance, we know a triangle is 180 degrees. So you actually, we can do this in pink. Triangle's 180 degrees. We know this, we should know that. But we use the formula, the sum of the interior angles. So let's actually write this up here. Ooh, probably should bring this down. The sum of interior angles of a polygon, any polygon that is, if you recall, is the equation n minus 2 in parentheses times 180. So if we took this triangle, for example, we know that there are 3 sides to a triangle minus a 2 times 180. This becomes a 1 times 180 is 180. And we could do this for any polygon, whether it's 8 sides, whether it's 100 sides, we could use this particular formula. Okay, so that is something we definitely need to be able to recall in today's lesson. Now, if it's a regular, let's say it's a regular triangle, right? That means all of the angles in this particular triangle are congruent. Okay, and we already know that there's 180 degrees. We use this formula and we already just knew it. But we take the number of sides. Well, once we have how many total the interior degrees there are in a polygon, in this case it's 180 degrees, we just divide it by the number of sides there are. So in this particular case, we would divide this by 3, and we would get 60 degrees, okay? But if you want a general formula for this, we would take this would be the equation for one interior angle of a regular polygon, okay? So if we took this and we said, okay, we know how to calculate the interior angle, the sum of the interior angles, and we just divide that by the number of sides there are, this would give you one interior angle of a regular polygon, okay? And let's just do, for example, let's do an octagon. We know an octagon, so this is a quick example here. Let's call this a regular octagon. Okay. In a regular octagon, we know that there are 8 sides, so we're going to say n is equal to 8. And let's calculate how many total degrees are there in an octagon. So we're going to say n minus 2 times 180. And we could say that it's 8 minus 2 times 180, which is 6 times 180, which is equal to 1,080 degrees, okay? So that's how many total degrees are on the inside. But what if we also wanted to find out what one interior angle is? Well, we would take that 180, or 1,000, I'm sorry, not 180, the 1080, divide that by 8 sides, and we should get that one interior angle is equal to 135 degrees. Okay, and that goes for all of the angles that are on the inside because they're all congruent to each other. Ironically enough, the exterior angle if you remember, this is a good refresher, right, it's supposed to be a 1, is 45 degrees, because these are supplementary. Exterior angle. Let's write that a little bit cleaner. The exterior angle, and these are supplementary if you recall. Okay, so a lot of things to recall. There's going to be 1.5-ish new definitions. Okay, so this is our recall. What's new is, what if we have, well, let's actually draw a new shape. Let's say we have a regular hexagon. Hexagon, as we know, is 6 sides. So let's draw a 6-sided figure. And obviously, I'm not going to draw this to perfect scale. It's very difficult to draw regular figures. And with the regular hexagon, we're actually going to draw the center of this regular hexagon. Okay? And we have 2 things that we are going to focus in on. Actually, I'm going to draw this, make this a little bit bigger, because I need more space. Sorry if you already drew it. But we have 2 things that we are going to be concerned with. I'm going to draw the first one in red. And the first thing is going to be this distance from the center of the regular polygon to one of the corners or turning points. And this is what we call a radius. Why do we call it a radius? Well, if I drew a circle around this piece, it would actually be the radius, right? Because a radius is the same distance all the way around. And obviously this is not going to be great because it's hard to, like I said, it's hard to draw a regular polygon. But let's pretend, let's just pretend that this is a perfect circle. Then this radius hits on all ends. Okay, so the radius is a segment from the center, that bisects the interior angles. Okay, so if you really think about it, it takes this angle. Let's say we could calculate that angle in a little bit. We will, but it's going to bisect that particular angle. More importantly, it connects to these turning points or these corners. Okay, the next one I'm going to draw this in green, and we're going to draw it from the center again down to the middle of this particular segment, or this, yeah, for this particular segment. And we actually call this is a new one, it's called an apothem. An apothem is a segment from the center, from the center of a regular polygon, that bisects, or let's say this, that is a perpendicular bisector to a side. Meaning, 2 things. 1, these 2 segments are congruent, and 2, it creates a 90-degree angle. Okay? So we have an apothem, and we have a radius. These 2 are going to be very important in actually calculating area, because we might be given a radius, we might be given an apothem, we don't know. Every regular polygon is different, okay? But here's where the equation kicks in. A regular polygon, no matter what it is, So the area, go back to black. Area of a regular polygon, let's say polygons, doesn't matter what it is equal to 1/2 times the apothem, so there's that definition, that new term, times the perimeter. And this is where we're going to have to calculate some perimeters too. Radius is going to come in handy on some occasions, but let's do this as an example. Okay, let's take this example and let's say that actually, let's leave it at that. We'll do some examples in class. Okay, so for now, let's leave it at that. All right, we have our equation for regular polygons, and we'll knock this out a little bit more as a whole. If you have any questions, please ask. Know these terms, be able to use them fluidly when we get to class. All right, I'll see you in the next one. Bye.